Here, we look at the first scenario, and we see that the length of the pendulum is much greater than the height of the object.
Mm-hmm.
Okay, so that tells us what?
Pendulum.
Okay, so where do we go from there?
So then from there we will find that our period is equal to 2 pi the square root of G over L. So yeah, give us L.
Okay. Now what do we do?
So then the second one is the physical pendulum.
Okay. What does that tell us?
So that means we can use the formula T is equal to 2 square root of mgh over I.
2 pi over, or times what? Mgh over I know this one.
The formula sheet that he gave us is the opposite.
It says mgd over I?
Yeah.
Is that for frequency?
No, that's for pendulum.
Huh?
That's for pendulum.
Yeah, I know, but is it period or is it frequency? It's
That's
frequency.
omega.
What's that?
It's omega.
Yeah, omega is angular frequency.
Yeah.
All right?
Yeah.
So omega equals 2 pi f.
Mm-hmm.
That's a relationship between period and
inverses of each other.
okay. So at this point, I need to find what does I stand for here?
Inertia.
Inertia, good. So we're going to have two inertias. What are the two inertias? Okay, so we have the inertia of the big sphere. Okay, so as this is going back and forth, since it's so big, the sphere is going to be spinning around, right?
Mm-hmm.
And because it's spinning around its own axis, we need to use the sphere inertia formula. What is that?
2/5 m squared.
Good. That's one formula. What is R in this case?
This would be the length of the string. It should be L over 2.
Distance was L over 2 as well, I believe.
Mm-hmm.
Probably. Was it not?
Yes.
Okay, so at this point, that distance becomes L over 2.
Mm-hmm.
Which becomes 1/10 L squared. That's I of the sphere. Now, what other inertia do we have? So regardless of the size, you have to think of the mass being concentrated here at the very center. Okay, so if you think of it that way, you can say, okay, well, I can find this whole distance is my new radius, and I can
L.
Yeah, and I'm rotating about this fixed axis. If the ceiling wasn't there, I'd be rotating in it. You see that? Like that?
Mm-hmm.
So that is just a rigid body that's rotating about a fixed axis. We just went over that formula. What was that?
mr squared.
Good, mr squared.
Okay.
Are you starting to understand?
Yeah.
What is R?
R on that one would be L.
L, good, because we go all the way to the center of mass. And then we add these two. Excuse me, I'm so sorry. I don't know where that came from. I'm actually well rested. And at this point, when we add them, if we find a common denominator, so I put in the 10 over 10 because this is a 10 and I need the common denominator. Does that make sense?
Yes.
Okay, so then I add them up. What do I get?
11 over 10.
Very, very good. This is the total center of mass of that system. So what happens? The masses, they go goodbye. And this sucker here cancels with this sucker up here. 11 over 10 L over G. all that under the square root times 2 pi. How does that help us?
The other one is
See, I
going
told
to be
you.
2 pi square root of G over L over G.
I told you.
Why don't we have G over L then?
Yeah, because I'll let somebody talk me out of the right formula. It's L over G, not 2 over, or G over L, like you said. You probably gave me the frequency formula again.
Mm-hmm.
If we have the right formula, I think you gave me frequency, right?
Yeah.
So at that point, what I can do is I can factor out that 11 over 10. So what does that tell me, though, if I have that formula up there?
And that tells you that the bigger bar is on just a little bit over the 1 over
Yeah,
something.
because this coefficient here is greater than 1.
Mm-hmm.
That means that the relationship C is the simple pendulum, 11 over 10, the physical pendulum, right?
Mm-hmm.
Actually, no. So because this side is longer, because this represented the physical pendulum.
Mm-hmm.
So this is larger, therefore this is longer. Any questions?
Mm-hmm.